And I just hope that my wife sitting here will believe half of it. It's my pleasure to be here. And Charlotte is not new to me. I've been here several places, and I love it. It's a beautiful city. And welcoming you here in North Carolina is an added pleasure for me. I'm going to talk today about activity networks. And my first, I have to pick something here and push it. And the title is A Guided Tour. And the reason why I picked the word guided tour is like when you visit a museum, they don't show you every picture and every statue, but they show you some interesting aspects of what you see. And I'm going to present to you some aspects of activity networks which are of interest to me and to my students and my colleagues we have been working on for some time. So let's start. Why activity networks? I wrote a book which appeared around about 1970, and the title is Activity Networks. And but why? And the reason is, it's an excellent model. By the way, can everybody hear me? Yeah. Yes? You can't? Oh, you can. Very good. And the second question is, can you see me? I don't stand behind this thing, otherwise you won't see me. Why activity networks? Why activity networks? And the reason is they are excellent models for representing many activities in real life. And I mentioned some of them here. And the first one, of course, is project planning and control, which is of interest to me. So in project planning and control, which are better known to many who are here under the acronyms CPM and PERT. So you talk to anybody in the real world and you talk CPM or PERT, and you know what you are talking about. And I'm going to talk about various modes of representation: scheduling under limited resources, project compression, which is shortening the project duration, and financial management. I'm not going to talk about many things, many other aspects of project planning and control, which many of my colleagues are interested in, such as personnel, project selection, which is portfolio selection, etc. It's a very wide field, and I invite you, and one of my ambitions in this talk is to recruit some of you to work on some of the problems I've been mentioning. So, this thing is supposed to work. Here it is. Project representation. Typically, you know about all this stuff, so I'm going to bore you for a few seconds and then I'll go to something more interesting. But the outline of the talk will be approaches to representation, the optimal project compression, which is shortening the project duration, and generalized precedence relations, which are somehow seem to be forgotten in the literature, and budgeting considerations. I'll get to it, hopefully soon. Now, they told me there is a gap between pushing the button and realization of the change. Here is the pushing button. Here it is. How is the project represented? Well, algebraically, and there's a list. That's how you talk to the computer. Adjacency matrix and the path arc matrix. These are known to many of you, so I'm not going to dwell long on it. And the second representation is graphically, and that's what most people are familiar with. I swear I pushed the button. Here it is. There is a Gantt chart. I was talking to somebody yesterday, and he said it's an ancient, which is true. It is around about 1920, 20 something, 22 or something, Gantt chart. An activity on node, an activity on arc, and the last one is the state space. Most of you are familiar with everything I have said up till now, but some of you will not be familiar, may not be familiar with the state space. That's a new concept which I would like to introduce to you, and then I'm likely to mull over the characteristics of that. So, here we go. This is my favorite network, by the way. I give it a name. I call it the interdictive graph, because it stops you from interdiction. It stops you from doing anything you want to do. And it exemplifies many things. It has 5 activities. They are numbered 1, 2, 3, 4. And what I have there in red are UDCs with uniformly directed cut sets. It's uniformly directed cut set. A cut set is a set of arcs which essentially separate the node, the origin node, from the terminal node. If you literally take a pair of scissors and cut those arcs, you separate the two. And I mentioned here, there are 3 of them in this network. The dotted line, I call this, the name given to it is uniformly directed cut set. Why uniformly directed cut set? Because all the arrows, and any one of these, all the arrows go from the set X to the set X bar, where X contains the source, and X bar contains the terminal. Are there non-cut sets which are not uniformly directed? And the answer is yes. And the next one will show you. That's the dotted line there. Come on. I pushed the button. Ah, here it is. Okay. The dotted line separates the origin from the terminal, but 2 arcs are directed in one direction, and from X to X bar. But the third arc directed from X bar to X, and that's all not uniformly directed. We are interested only in uniformly directed cut sets. Okay. Here is the state space. Here is my graph, the 5 activities, and the state space is very helpful in interpreting the progress in case of stochastic duration. Remember PERT. The difference between PERT and CPM is PERT introduced the concept of stochasticity and randomness in the duration of activity. And therefore, you start with 1 active and 2 active, and then you proceed to, I have a pointer here. When you start at time 0, you start with both activities 1 and 2. Activity 1 and activity 2, both of them are active, and this is the first set. So if you take a picture of the project, you will find 1 active, 2 active. And then either 1 finishes first, please remember everything is an unknown, or 2 finishes first. If 1 finishes first, then you move to this state. When 1 finishes, you can start 3 and 4. And therefore you have 2 active, 3 active, 4 active. If 2 finishes first, nothing happens, because you can't proceed. So when 2 finishes first, you get 1 active, still going ongoing, but 2 is dormant. Dormant is asleep. Okay. And then you go on. If you have all 3 of them, either this finishes first, 2 finishes first, or 3 or 4, and that's why you have 3 branches in here. And as each branch is realized, you either move to a new set when 1 of them is dormant, or to a new set, a new node, which is a new state. So for example, here 4 is dormant. 4 is dormant means 4 finished. Well, 2 and 3 are still active, but 4 is dormant, and that's a state. If you will take a picture of the project, you will find that 4 is dormant, nothing can happen. But 2 and 3 are active. Now when 3 is finished, still there's nothing you can do until finally 2 and 3 are finished, and then you get 5. Well, here is the full spectrum of the state space, which is I'm too hasty. Okay, here is the full spectrum. There are 12 states. There are 12 states, and this state here is the start state, and this is the terminal state where no activity is active. And there are 12. This is very well known. This has been well known, at least to me and my colleagues, for a long time. And then, around about 1980 something, Professor Kulkarni and his student, Kulkarni is here, by the way, sitting here, they suggested that suppose that these activities are exponentially distributed. If they are exponentially distributed, you see what I did? I pushed the button, and then when I push it again, see nothing happened. Here it is. If they are exponentially distributed, then you have a continuous time Markov chain. That is very clever. And that leads to a continuous time Markov chain analysis. You are now in a domain of mathematics, probability theory, which is very well established. And they derived certain relations. By the way, the distribution of the completion time of the project is very well known, and for some time, Marcel Nutz has provided that. But their contribution was to develop recursive formulas for the expected values, the k expected value. So if you want the third expected value of the completion of the project, or for that matter, any node in the project, you can get it recursively, and that's very clever. You don't have to do the integration, because the integration has e to the power, and e to the power of a matrix, that's not very easy to evaluate. So that was a very, very important reference. That is, the paper is by, I will give you the reference at the end, but the paper is by Kulkarni and Adlaha. Adlaha is his student, and she's now a professor somewhere. Yeah. Okay. So now we know that if you have a graph, and if the activities are exponentially distributed, then it falls in the domain of continuous time Markov chains, and therefore you can very easily secure the moments of the, not very easily, but easily, of the completion time of any node, realization time of any node in the project. Now, what I'm going to do here, we have done some work, and this is, I tried to cite here some of the people who worked with me, and one of them is Girish Ramachandra, who is now in India. He's a big chief, he's making lots of money. And Adam Rudolph is here in America. And he was working for a company, but he wants to change. So, okay. Here you are. Here is an example. I'm citing this example because I want to, as I said before, I will depart from standard talks, plenary session talks, by presenting to you problems that are bothering me, and I hope to recruit some of you to contribute to it. So if you have this graph, this activity network, and here are the lambdas of the exponentials, and the average durations, just 1 over lambda, and then you can get the continuous time Markov chain, the continuous time Markov matrix, which is the rate matrix. It's different from the standard discrete time Markov matrix, where the sum of the rows, the entries in the row add up to 1, because the probability of moving from one state to another state. Here, this is the rate and therefore the sum adds up to 0, because you can stay in a particular state. Okay, I'm just reviewing for the benefit of some of you what on earth is that continuous time. Here it is. Here is the matrix for that. And I would like to draw your attention. And I highlighted some cells here. This is number 2. Number 2 appears here, and here, and here, and here, etc. I highlighted that for a particular reason, and I'll mention that in just a minute. So here's the matrix, and you can get all sorts of results from that matrix. Okay. And I list in here, I don't expect you to follow this. This is standard stuff, very well known about the derivation or the duration of the project. So, and if I assume here, for simplicity, that there is a cost attached to doing any activity, it depends on the resource you allocate to it, and the resource is written, expressed as X sub A, which is the amount of resource in activity A. And so there is a cost of the resource added or used in the activity, and there is a cost of tardiness. You can add to it the cost of earliness, but I didn't do that. And the reason is it's just an extension. But tardiness is very interesting. And then you are interested in the expected cost. You don't have to be interested in the expected cost. You can be interested in other parameters, but the expected cost is agreeable to so many people, so I picked it. So here is the expected project cost. Is the first term is the expected cost of the duration, which is the resource times the duration. And here, this is the cost of the rate of tardiness. So it costs you $1,000 a day if you are tardy. And now you have the integration of the time the project actually finishes minus specified time. This is T sub S is a specified. This project is desirable to finish, for example, in 18 months. So 18 months from now, that's TS. If you finish it beyond that, then there is a penalty. And by the way, I worked in a project like that, and there was a penalty per month, and the penalty was very heavy. It's about 1% of the value of the contract. So it is not negligible. Okay. And what I write here is an expression that is the probability, the density, probability of finishing the project at time t. This is well known, but this is the expected value. I draw your attention to it because the matrix T in the exponent of E is the transient matrix of the continuous time Markov chain. So you have exponential to a matrix, and when you evaluate that, you get the function, which is the expected cost. Now comes the issue of project cost control. Suppose you don't like, it is very expensive, you are tardy, you are too tardy. Remember, everything is stochastic. You are too tardy, this is optimization now. And you would like to put more resources into some of the activities in order to speed it up. Question is, which activities you should invest in? That's number one. And number two, how much? But please remember how much in order to impact the expected cost. But the expected cost is a function of the completion time. And the completion time, you get it as a function of the transient matrix. And that if you change the allocation to one activity, like activity 2 that I presented to you before, you change many entries in that matrix. And that's very difficult. What you are interested in, to put it briefly, what you are really interested in is to answer the first question. is the partial derivative of this expected cost relative to a change in this T matrix of one element. Not one entry, but one element, one lambda. And therefore, but that shows in so many entries, and that's very difficult. When we did that, we did it by brute force. We emulated, after all, what is the derivative? It's delta y over delta x. Everybody knows that. So that's what we did. We added a little bit to each activity, possible activity, and we got evaluated the function, evaluated for each one of them, and then picked the one which gives us that's brute force. And how to get that differential, partial differential, is an open question. I don't know. And I invite you to contribute. If you can get me, I have said this, I have stated this problem to many of my colleagues. Please help me. I have a matrix, I have a function of e to the power of that matrix. If I change one lambda, it shows in so many entries in that matrix. What's the partial derivative relative to that lambda? Okay. I hope I'm not boring you, but I hope I'm recruiting some of you to do something here. I really am stuck. I don't know what to do. Okay. Here it is. Now, here is the statement of what I just said, and the issue at hand is how to rank the activities related to importance, because we want to invest more resources in the activity that impacts the duration the most. And second, how to evaluate the partial derivative, which I just explained in a minute ago. Here it is. What happens to distributions that are not big? Suppose that, remember, all this is based on the assumption that the distributions are exponentially distributed. But suppose they are not. In fact, those of you who remember, the originators of PERT assumed the beta distribution. They never spoke about the exponential. And when you think about it, you talk to any manager and say this is exponentially distributing, he thinks you are crazy. Nothing is exponentially distributed. It's convenient for us to work with the exponentials, but nothing is exponential. Okay, so suppose it is not. And I'll try to mention people who are working with me on this. Chen Day is here, I think. He is working on this problem with me, but we need help. The answer is very simple. Use phase-time distributions. People know about that. Probabilists and statisticians know if something is wrong. There is a theorem somewhere which says that any distribution which has a rational Laplace transform, which is almost all the distribution that you and I will work with, can be represented to any degree of accuracy with a phase-time distribution. There are phases. The phases are stages, and each stage is exponentially distributed. Okay, so now that's a very powerful thing. You want you don't like the exponential because it's not realistic, or you have your own distribution and you want to represent it. Well, for heaven's sake, you can do it, and you can do it with in phase distributions. Okay. Now, I'll go very quickly over this. These are different kind of phases. The series here leads immediately to the Erlang distribution. And the series with different lambdas, which is here, leads directly to the generalized Erlang distribution. Okay? A lot is said about the Erlang, very little is said about the generalized Erlang. But here is an exceptional one, which is you start at this stage, but you can proceed to the next stage with a certain probability, or you can go out. And at this stage, you can proceed to the next stage with a certain probability, or you can leave the system. And this leads to a particular representation. Well, it doesn't take too much work or too much intelligence to generalize this. Why? This was done by somebody, and it is very easy to generalize it. If you have hypo-exponential distributions, which are the coefficient of variation is less than or equal to 1, less than 1, because equal to 1, that's the exponential. And you get this series here. If you have a hyper-exponential distribution, you can have them in parallel with the coefficient of variation greater than 1. And of course, you immediately let your imagination run wild, and you end up with all sorts of distributions. The question is, you have the alphas, which is the probabilities going somewhere, and then you have the lambdas, because these are undetermined right now. And the question is, how do you determine the alphas and the lambdas to fit, to end up with a distribution which fits best the distribution that you have? So you have a beta distribution. Now, which alphas and betas will give you the closest to it? And the question comes is, what do you mean by closest? How do you measure closeness? Well, I will not dwell on that, but there are 2 or 3 measures of closeness. And the one I like most is the entropy, the co-entropy between 2 distributions. But that's, I'm not going to talk about that. Okay. I wanted to present this to you because our beloved colleagues in statistics don't like something and I like it. And that is approximating distributions by method of moments. They don't like it. They like the, there are 2 other methods. Yeah, I remember them. I pushed them. Here it is. The concept now is very easy. From the continuous time district matrix, secure the expression for the k moments. All right. Now, you have your k moments, and now secure the optimal solution to the resulting mathematical program. And typically, it's not a linear program, but you can still do it and test the solution for precision, and that's what I was talking about. How do you measure the error that you have made? Now, we have done some work. I'm not going to dwell on that at all, but we took 2 stages with lambda 1 and lambda 2. Here is the matrix. There are 3 stages, and these are 2 curves that we approximated, and I go on. I mean, this is the y1. I can see very well. And this is for k equals 2, or 3, or 4, and of course lambda is equal to q per number. The experiment. So what you have is it's either 1 stage, 2 stages, or 3 stages you approximate with, but they are all linear. So, and this is the figures you get, and I leave it to you to respond to the question, how do you measure the accuracy? Which one is the best, you think? Is it eyesight? Do you eyeball the stuff, or do you have a measure for the error committed? An analytical measure. Oh, the price paid for this concept of phase distribution is the vast expansion of the state space. That's why I started this talk, this aspect of the talk, this part of the talk, with talking about the state space. You start with 12, if you, in the IG, the interdictive graph, and you have a state space of 12. If each activity now is represented by 3 or 4 stages, the number of states expands. It increases fantastically. in the report in the paper by Kulkarnia and Laha, I think they dealt with a 48 activity project, and they ended up with something like 250,000 states, and that's assuming exponential. If you don't have an exponential, that will be 10 to the power of something. And can you imagine a continuous time Markov matrix of 10 to the power 20 states in it, or 10 to the power 30? It's impossible. And the question, this raises some questions related to it. Now, how do you ameliorate, how do you deal with the vast increase in the state space? Well, just think for a moment, and we'll immediately come up with 2 or 3 answers, and here they are. The tunneling approach, what I call the tunneling approach. For heaven's sake, from any state, don't enumerate all possible states that can be reached from there. Enumerate only the important ones, and the one that's most important, which makes sense to many of us, at least made sense to me, is the one that will be realized soonest, which, if you recall, that is very similar to the idea of the closest city in the traveling salesman problem. You don't enumerate all possible cities you go to, alternatives, but you enumerate the closest city. And the same concept here. You go to the state that comes next, which is the closest. I call this the tunneling approach, because you limit yourself to a tunnel, your vision to a tunnel through that network. And sure enough, you end up with a tunnel here. Here it is. With these numbers here, with this data here, from this state you go to this state, from this state you go to this state, this state, this state, this state. And of course you have 5 activities, and you end up with 6 states, of course. The bad part of it, I call this T1. T1 is the tunneling 1, which is the myopic. You go to the closest one. Very similar to the traveling salesman problem. The T1 approach has a worst case performance bound of infinity. It is unbounded. It's a very bad one. In other words, it means the following. You use this heuristic, and I can give you an example where the solution that you get with the heuristic is 10 times the optimal solution. If you wish, I can give you another one which is 100 times the optimal, or 1,000 times. It's unbounded. Which those of you who remember the traveling salesman problem, that's exactly the same result that you get into the traveling salesman problem. The closest city heuristic of the traveling salesman is an unbounded heuristic. It can be arbitrarily bad. Okay, so that's no good. What is the next idea that comes to you immediately? Well, for heaven's sake, don't enumerate the closest city, enumerate the closest 2 cities. So that's the tunnel 2, T2. Don't go to the one that happens soonest, but the 2 that happens soonest. And I did that. We did that. Here it is. And as we say back home, it didn't do nothing. Here it is. The same number. You see, 12 states with only 1 branch deleted. So you do not save anything in the state space. So the T1 can perform very poorly. The T2 may not save you anything. And the question is, what can you do? I don't know. And I hope you will be interested to answer that question. Suppose you want, very much like the traveling salesman problem, suppose you want to adopt a heuristic that cuts down on the size of the state space. What heuristic would you use? The T1 is no good, the T2 is no good, so what do you do? Okay. So I continue this now, and here is the aggregation approach. When, for heaven's sake, don't take the network as given to you, aggregate them. Aggregate some of the activities together and act as if it is one activity. That's the aggregation approach. Okay. So here it is. I took 1 and 2 activities. This is 1. Here is a cut set. And 1 and 2. This is activity 1. And I'm not going to delete everything. Here it is. I start with 2 active, 3 active, 4 active, etc. Well, I end up with 10 states instead of 12 states. Big deal. I tried this with this approach with different networks and the savings. First of all, the question is, how do you aggregate states? That's a question. It depends on the topology of the network that's given to you. And second, when you are done aggregating the states, you get a result. How good is that? It's an error, it's an approximation. How good an approximation is it? That's all. Okay, so here is the moral of the story thus far, and I have about 10 minutes to go to get it for me. And I have about half an hour or something to do. Anyway, the tunneling 1 is no good. The tunneling 2 does not say much. The method of moments, which is discarded by many researchers, many statisticians don't like method of moments. I like it. I think it's the only way we can go. And the result is a nonlinear programs, which are maybe sometimes are very difficult to solve. And the aggregation approach appears to be topology dependent, depends on the person. The question is there a general rule for aggregating those states? And I don't know. And I leave you that. Okay. In everything I have said up till now, including but not not in the Markov stuff, the activities, even in the Markov stuff, the assumption is that an activity starts as soon as it is sequence feasible. Remember, I started in this thing here in the state space, 1 active, 2 active, meaning the 2 of them are the moment they are available, and therefore you can start them. And as soon as 1 is finished, you can start 3 and 4. You should start 3 and 4. So, as soon as it is sequence feasible, you start it. Suppose it is not. And the second one, all the activities must be performed. If you are given a PERT CPM or CPM graph, all the activities have to be performed. Suppose that's not true. And you end up with the generalized activity networks. Now, this is something I worked on around about 1960 something. And there are the deterministic part and the stochastic part. And I'll go very quickly over this because I don't have time. The deterministic part, you represent a start-to-start restriction, start-to-finish restriction, finish to start, and finish to finish. I'll illustrate this in just a minute. In the stochastic, I have a receiving end and an emitting end. Let me talk about this first. I apologize, I have to go fast here. Here is the start to start. So the start of B, this node here, the start of B, must be at least delta time after the start of A. I leave it to you to imagine situations where this is realized. For example, if activity A, for example, has 100 units, it's not one thing, but you are producing 100 units, and activity B is the second phase of working on those units. You can start the second activity after, for example, 10 or 15 units of the first activity have been completed. Then you transport them, and then you start. And now, machine B can be continuously employed. So that would be an interpretation of what you mean by start to start. Now, the rest I'm not going to explain, but you can imagine scenarios where each one of them is realized. And then generalized. Remember now, as soon as, it is not as soon as A finishes, B starts. It's not true. There is a restriction on the start of B after the start of A. And now this is the finish to start. This is start to finish. And of course, finish to finish. Well, you start and finish and therefore. Okay. The point is, I discussed this with some colleagues. I should have mentioned this one. It will come in a minute. You can translate everything. You can leave start to start as is, but anything that goes to the finish node, you translate into the start node. So now you have everything going to the start node. And the result is, here is, I have in this example, I have 10 activities. This is the last activity 10. And here is an activity, there's an upper bound and a lower bound on its duration. And here is the marginal cost of this. This is infinity, meaning that activity number 4 takes 10 days to complete, period. You cannot shorten it. And therefore, this is reflected in a marginal cost of infinity. So that's the meaning of infinity, just in case somebody picked that up. And here are the list of the generalized precedence activities. Question: what is the completion time of the project? That's easy. The second question is, suppose you don't like the completion time of the project. How do you compress it? That's the compression. Okay. And this I wanted to mention to you. This is jointly done with Dr. Taragian. He is in Ferdowsi University in Mashhad in Iran, and Dr. Chi Jianon, and he is in China in the Northern Electric Power University near Beijing. And he was visiting me, and so was Taragian. And we work with remotely. But he did it, and I translated this, translates everything into FS. Nothing goes to FF, nothing goes to F at all. And the result is of compression is available. Here is the cost curve. This is the current duration at zero cost, and this is the rate, then an increased rate. As you, those of you who are familiar with Fulkerson's work way back in 1961, you end up with a convex, because I assume linear, and you end up with a convex increasing function. So you get the same thing here. Okay. So that problem is solved under generalized precedence relations. So we seem to have a good handle on optimal project compression under deterministic GPRs. How about stochastic GPRs? And the answer is that is an area that nobody has knows much about. And the next few graphs, I will not dwell on them at all, explain what I mean by stochastic. This is the receiving end, and this is the terminal end, and you can have the node will be realized if any activities coming into it is realized. Any one. This one is one and only one is realized. This one is the standard one, which is, we know, both of them have to be realized. And the same thing with the exit part of the node. Both of them have to be undertaken. One of these has to be undertaken. You may, this model, we have used this model in study, practical study, where I can't talk about it, something about defense standard. the only way to represent the problem is actually to represent it through a stochastic generalized precedence relationship like that. But that field is completely, nobody has done anything about it. Whether it is estimation of cost, this is, all this algebra is known. But optimization is not yet. I should ask for extension of my talk because I spent so much time waiting for this. Okay, this is an example. It is published. It's written by Eisner, and I just transform it into the model I represented here. And this is my the GAN, Generalized Activity Network representation, but I'm not going to say much about it. The next one is very, next topic is very little time to explain, and yet it is fascinating to me. I tell you, I got that impression watching the forecast of a hurricane. If you look at the TV for the forecast of the hurricane, you'll find they start somewhere in the Caribbean, and then there is what I call a bugle of possible path of that hurricane. I don't know if you have seen that or not. There's a possible path. And I thought, wouldn't it be nice if that's the OR people, can present the project manager with a chart like that. Here is where you are, and here is the bugle. This is the expected possible path of your project given randomness. So that's the motivation. Okay? Now, under deterministic, here is the one, you build a Gantt chart, and from the Gantt chart you know that at this point in time both activities are working, so the level is 2. In this interval of time here, only activity 1 is working, so that's level is 1. I'm simplifying the cost. The cost is exactly equal to the time. If you don't like that, you can dream up any cost function you like, and you complicate your life. But this is very easy. And in this interval here, it's 2 units, and then from now on, it's only 1 unit, and you end up with this curve. That's deterministic. Okay. How about the stochastic part? Well, this is the same picture again. And now you have a project, you estimated the expected cost to be 17.5, and you would like to have 40% markup, which is about 7. And now you bid for 24.5. Instead of 17.5, you bid for 24.5. And now you receive money during the existence of the project, and here it is. You get 5 at the start, 5 at 5, 5 at 10, 8 at completion, which is under deterministic condition is forecast to be 12.5, and 1.5 typically is kept by the owner as guarantee that everything goes okay, and you will get it 1 month later, 1 period later. Okay. So the total payment is 24.5. So now, if everything is deterministic, you know the path of the cost, and you know the path of the payment. And I give a diagram here. And here is the cost figure. And here is the payment. 5, then another 5, then another 5, then an 8, and then a 1. And you notice the yellow part, this one and this one, you are paying more your expenses, your out-of-pocket expenses are more than the receipts. The dashed part are your funds coming to you. And then the rest is, obviously you're not going to get the 7, because when you borrow, you pay interest on the money that you borrow, and you're not going to get the 7 that you have. How about stochastic? Well, the intuitive bounds on this is that you have well, let me here it is. Here are the bounds. This is the optimistic lower bound, and this is the experimental lower bound, and this is the pessimistic. The blue and the green here are the pessimistic, and here is the experimental. Now here is the Google I was talking about. You tell the manager that at t equals 5, your cost can be as low as this and as high as this. And at time 10, the same thing. At any point in time, not at any point of realization of a node, but at any point in time, this is the status of your budget. And this diagram here shows you, this is the blueprint. These are the payments. And you can see, I pointed out here that the realization of these 2 points is a random variable. But even as it is now, you can see that at this point in time, you can be almost half the time okay, but almost half the time you are not okay. It's above. Here, the cost is more than the receipts, and here the receipts exceed the cost. Now, I have to stop here. I summarize all this in the write-up, and the question still remains of, well, what happens if you have, can you get an analytic, we got this by Monte Carlo sampling. Can you see an analytical solution to this? This is our conclusion. I don't know. Well, thank you very much for listening. I hope I didn't